All right, so moving right along. In this section, what we're going to do is talk about the graphs of quadratic functions, which might seem kind of intimidating, but the good news is we're really just going to apply what we learned in the function transformation section to a specific family of functions. So for example, back when we were talking about function transformations, I might tell you that the graph of y equals x squared looks like this, passing through the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And from that graph, I might ask you to come up with the graph of, for example, 2 times x minus 4 squared minus 2. And if you were really good in that section, you might recognize that there's 3 different transformations going on here, 2 of which we refer to as vertical transformations. This 2 out here is a vertical transformation, and this -2 out here is also a vertical transformation. But this -4 that is affecting the x as opposed to the x squared is not a vertical transformation, it's instead a horizontal transformation. So the idea is, if you start out with this graph in red, you can just transform it 3 different ways. The first 2 ways are vertical transformations, and the other third way is a horizontal transformation. For the vertical transformations, we want to first multiply all of the y values by 2. Even though a lot of books would describe this as stretching the graph vertically, hopefully I made the argument that it's a little bit easier to think about it as we're taking all the old y coordinates and multiplying them by 2 because of this 2 right here. And then after we do that, we'd have to subtract 2 from the resulting y values. And that's because of this -2 at the end. Vertical because it's happening after this squaring here. After you've taken care of all the vertical transformations, you might notice that you still have horizontal transformations to deal with. Only one in this case due to this -4. Because it's horizontal, we're going to be affecting the x coordinate, not the y coordinate. And you might think that you should subtract 4 from all the different x coordinates, but because horizontal transformations, loosely speaking, are the ones that are the kind of backwards of what you'd expect, this -4 actually tells us to add 4 to all of the old x values. So we have these 3 transformations. I might as well apply them. We're going to take all these old y values, multiply them by 2, and then subtract 2. So this y coordinate is currently 4. 4 times 2 is 8, and 8 minus 2 is 6. So this point E is going to end up at this purple dot here, kind of taking this path to get there. Similarly, this point A has a y coordinate of 4, and so 4 times 2 is again 8, minus 2 leaves me with 6. So point A will end up right here. Points B and D both have a y coordinate of 1, so when I multiply them by 2, they get up to 2, but then when I subtract 2 from that value, they end up down here at 0. And because 0 times 2 minus 2 is -2, this point C is going to end up down here at -2. If I were just applying the vertical transformations, my graph would end up looking something like this. However, I'm not just applying vertical transformations, there's also this horizontal transformation, so I'm going to take these 5 purple dots and add 4 to all of their x coordinates. So now when I look at this dot right here, I'm not looking at its y coordinate, which is 6, but instead its x coordinate, which is 2. If I take 2 and add 4 to it, I get 6, so this dot is going to move out here to this point at 6, 6. Similarly, this point right here has an x coordinate of 1, and 1 plus 4 is 5. So it'll end up over here at 5, 0. This point, which has an x coordinate of 0, when I add 4 to it, ends up at 4. This point has an x coordinate of -1. -1 plus 4 is 3. And finally, this point that has an x coordinate of -2, when I add 4 to it, ends up over here at +2. I take these 5 green dots and connect them with the shape that I started out with in red, and I end up with this graph in green, which is my final answer. If the question was just to come up with the graph of f of x equals 2 times x minus 4 squared minus 2, all I'd have to do is start out with this standard parabola in red and apply these 3 transformations. And maybe you're like, yeah, great, I learned all that in function transformations. Where's the new information? Well, there's kind of 2 pieces of new information. The first one is just vocabulary. When we were dealing with function transformations, we didn't use terms like vertex or care a whole lot about x and y intercepts. But now that we're studying the graph of these quadratic functions, we're really going to be concerned with these 3 things. All you need to know about the vertex of a quadratic graph is it's the point where the graph, kind of loosely speaking, turns around. So in this initial graph in red, the vertex is at the origin 0, 0. When I transform the graph vertically to produce this graph in purple, the vertex moved down here to 0, -2. But the graph in purple wasn't the one I was interested in. My final answer, which included all 3 of the transformations, is the graph in green. And the vertex for the graph in green is right here at 4, -2. It's not just the vertex I'm interested in, though. I'm also interested in the x-intercepts and the y-intercept. For the x-intercepts, we're looking for where the graph crosses the x-axis. And you can just kind of see in the picture here that this graph crosses the x-axis at 3 and 5. So you could say your x-intercepts are at 3 and 5, or if you wanted to state them as points, you might say one x-intercept is at 3, 0, and the other x-intercept is at 5, 0. And maybe if you're kind of the contrarian type, you might have a bit of an issue with that and be like, yeah, in this case it's 3, 0, and 5, 0, but you kind of got lucky. It almost seems like you picked these transformations very carefully so that 2 of the original 5 points will end up exactly on the x-axis. What if I hadn't gotten so lucky and those points and didn't have 2 points that ended up right on the x-axis? How would I be able to figure out the x-intercept in that case? Well, it turns out not only can you get it geometrically, kind of by looking at the graph here, you can also solve for your x-intercepts purely algebraically. So if I take my original function here, f of x equals 2 times x minus 4 squared minus 2, and sort of think about what it would mean to be an x-intercept, well, an x-intercept happens when I cross the x-axis. The defining characteristic of the x-axis is all the points on that axis have a height of 0. The height is the y-coordinate, the output to the function, the f of x. So if I want to solve for what points end up on the x-axis, I have to solve for what inputs make the output for this function equal to 0. And fortunately, I can do that. The output for the function is 2 times x minus 4 squared minus 2. And I want to know where that equals 0. Well, I just solve this equation. Maybe add 2 to both sides first, then divide both sides of the equation by 2, and get x minus 4 squared equals 1. From here, if I wanted to isolate this x, I'd take the square root of both sides of the equation, but be a little bit careful. A little rule that a lot of students forget is anytime you decide to take the square root of both sides of an equation, you got to put in this plus or minus right here. So x minus 4 is not equal to the square root of 1. X minus 4 is equal to either plus or minus the square root of 1. But the square root of 1 is just 1, so I get x minus 4 equals plus or minus 1. So either x minus 4 equals positive 1 or x minus 4 equals negative 1. If x minus 4 equals positive 1, when I add 4 to both sides of the equation, I get x equals 5. If x minus 4 equals negative 1, when I add 4 to both sides of the equation, I get x equals 3. Note that this 3 and this 5 are the 2 inputs that would lead me to an output of 0. Therefore, they're the 2 points on the graph where the graph crosses the x-axis. They're the 2 x-intercepts that we saw down here geometrically. And yes, it's a lot easier to just look at the graph and figure out what those x-intercepts are in this example, but maybe you can imagine a similar example where the graph happened to cross the x-axis at fractional value. It might be really hard to estimate those fractions just by looking at the graph, but we can always calculate them exactly by doing things algebraically. One more piece of information that we need out of this section is the y-intercept of the graph. It's a lot like the x-intercepts of the graph, except instead of trying to figure out when we cross the x-axis here, we try to figure out when we cross the y-axis here. Well, unfortunately, in this case, if we look at our graph in green, it's not going to cross the y-axis until way higher up. It doesn't look like it even fits on this page. So it's hard to just look at the graph and tell what the y-intercept is. Fortunately, just like there was a way to figure out the x-intercepts algebraically, we can figure out the y-intercept algebraically. Since the y-intercept is just the point on the y-axis where the graph crosses that axis, and the defining characteristic of the y-axis is it's not over to the left and it's not over to the right, it's kind of right in the middle. Any point on the y-axis has an x-coordinate of 0. To figure out the y-intercept, all we have to do is figure out what output is associated with an input of 0. In other words, all we have to do is evaluate f of 0. Unlike the x-intercepts, where we were trying to figure out what inputs make the output 0, with the y-intercept, we want to figure out what output come from an input of 0. That's a little bit easier. To evaluate f of 0, all we got to do is copy this blueprint right here, but change all the x's we see into zeros. So f of 0 would be equal to 2 times 0 minus 4 squared minus 2. 0 minus 4 is negative 4, and negative 4 squared is 16. So it's 2 times 16 minus 2. 2 times 16 is 32. 32 minus 2 is 30. So the y-intercept of this graph happens at 30. Or if you want to write it as a point, we could say it happens at 0, 30. It doesn't show up on my graph here, but if my graph continued all the way somewhere up here to 30, we'd see that this graph in green crosses right here. And you're like, all right, great. That's a lot of information, but I think I finally have it. Well, not quite. Maybe you remember I said there's 2 more things to know. One are these vocabulary words, the vertex, the x-intercept, and the y-intercept, and how to get them from this graph. But the other thing is kind of a bigger deal, and it's going to take us several videos to learn how to do. Turns out that it's not this function that we want to be able to graph, it's this function that we want to be able to graph. F of x equals 2 times x minus 4 squared minus 2 is in a very useful format. It's in a format where we can kind of see the different transformations. But this function, 2x squared minus 16x plus 30, is not in a useful format. We don't currently have the ability to graph this function. I mean, I guess we could plug in inputs and outputs and get an idea of the graph that way, but we certainly don't have the ability to use what we learned about function transformations to learn what this graph looks like. But look what happens if I take this equation, whose graph we do know how to come up with, and expand things. X minus 4 squared just means x minus 4 times x minus 4. And maybe if you're really good and remember the acronym FOIL, you're able to change x minus 4 squared into x squared minus 8x plus 16. And if you are, you might think to take this 2 and distribute it through the parentheses just to get rid of parentheses. And if you did so, you'd get 2x squared minus 16x plus 32 minus 2. And since 32 minus 2 is 30, this function is just equal to 2x squared minus 16x plus 30. Which, not so coincidentally, is the exact same function that we have over here. My point is, if we start out with this function, we don't know how to come up with its graph. However, if we start out with this function, we do know how to come up with its graph. And since I just showed you that these are actually the exact same function, if we can just learn how to change this format into this format, we'll be good to go. Unfortunately, that's a pretty big challenge. Changing 2 times x minus 4 squared minus 2 into 2x squared minus 16x plus 30 is fairly easy. I just did it right here. But unfortunately, changing 2x squared minus 16x plus 30 into 2 times x minus 4 squared minus 2 is really hard. And that's the direction we need to be able to go. Because in this section, we're going to start out with quadratic trinomials that look like this, and our goal will be able to extract all the information from them that we're able to get from quadratic trinomials that are written in this format. So in the next few videos, I'm going to teach you how to go from this format to this format.